and all those sorts of things. And he is basically our expert when it comes to SEC protein analysis. The webinar will be recorded as usual, so if you want to have access to the webinar at a later time, you can request. After the webinar, there will actually be an email being sent out that gives you access to the recording. If in addition to the recording of the webinar, you would like to have access to a PDF of the slides, you can request those in an email to either Torsten or myself. I will be displaying the emails at the end of the webinar. The webinar itself is interactive but non-interactive, meaning you are more than welcome to ask any question you have during the webinar using the Questions tab on the GoToMeeting app. However, we will be having the Q&A session at the end of the webinar. So if there's any further questions in between, don't hesitate to ask, but we will answer them at the end. Also, the webinar will have a little self-evaluation session roughly in the middle, where you and we can check that actually what we told you hit home. So that's in a way more for us than for you, maybe. And after the webinar, you will also be asked to give feedback. I think there's an email that automatically gets sent to all people that have registered, and we would very much value your feedback. So if you can spare a few minutes after the webinar to answer that small poll, it would be very much appreciated. And with that, I guess I'm going to hand this webinar over to Professor Hofer, who will be talking about SEC protein analysis. Torsten?
Yes. Derek, thank you for your very kind introduction. Hello to everybody. Good morning, good afternoon, good night, wherever you are. I'm more than happy to present you today some of our thoughts and ideas about SEC protein analysis. And I would like to start immediately to get into detail with you and to let you know what we are going to talk about during the next roughly 45 to 60 minutes. So I would like to give you a short introduction. I would also like to spend a few minutes on the fundamentals of SEC, and I will spend some time of the SEC method development, because this is important to give you an idea how you can improve your measurements or your setup in order to get better results and more reliable and more detailed results for protein analysis. I will also talk about instrumentation, what kind of additional detectors can be used and what they are good for. And at the end, and this is pretty much the second or the last third up to the second half of my talk, is that I am going to show you a couple of applications for protein analysis using SEC, and of course at the very end, last but not least, I will summary and conclude what we have talked about today. On the right hand side on this picture you see the distribution of the participants of today's webinar, and as you can see there are this is quite almost a Gaussian distribution. So we do have absolute beginners, we have users, and we have experts. But basically, most of the users for today's webinar are non-experts. And this is one reason why I thought I should also start with an introduction of the SEC after I have introduced my topic for today in general. So when we talk about protein analysis and we talk about proteins and what can you do with SEC, basically what all of you know about proteins is that we have, as indicated here on the left hand side, we have these many various structures from the tertiary to the ternary, the secondary and the primary structure. A protein can fold up in order to have this full activity in the globular, so-called globular structure. Proteins are quite complicated polymers compared to or so-called biopolymers, and compared to the synthetic polymers, they are more complicated to handle on because they are made out of many, many different monomers. The monomers are called amino acids for the proteins. And last but not least, and this makes it even more difficult, these monomers can be these amino acids can have charges, and when they have charges, so we deal with proteins in terms of either these proteins are negatively or positively charged, depending basically on their so-called isoelectric point. When you have found this isoelectric point for protein, you can measure it in the overall charge sum of 0. This is the point you should look for protein analysis when you do SEC measurements, because then you will get rid of most of the possible interactions. So when you do protein analysis and using SEC as a method, this is what you can basically discover by using the method. Proteins are, as mentioned before, globular in structure, and they can show up as monomers, as you can see on the left-hand side, or dimers or trimers, or higher kind of aggregates in terms of the proteins. Those are the so-called impurities of the proteins, because the activity of the protein given for any biomedical applications is mainly given by the monomer. So one of the major questions is, how can I distinguish a monomer from a dimer, and how can I quantify it, and how can I measure the degree of polymerization, the degree of association in terms of how pure or how unpure my protein is or can be. So secondly, very, very interesting for SEC analysis is the analysis of the so-called monoclonal antibodies. One of the typical structure of the antibody is seen on my picture on the left-hand side. Antibodies are built up of out of various proteins, and these proteins are connected by disulfide bonds or bridges in between. And in general, if you put it if you look at it from a more general point of view, you have so-called heavy chain. These are the red-colored chain, and you have so-called light chain. These are the blue-colored chain. They are different in molar masses, and overall, your overall monoclonal antibody is also different in molar mass and different in size compared to the single heavy chain or the single light chain, and also different in terms of size compared to fragments of your monoclonal antibody when you fragmented it. And monoclonal antibodies are very well known in therapeutical use because they can bind to targets, target cells or proteins, and they can help they are designed to act as specific, to act and bind specific on any surfaces and can help to heal any kind of or some kind of health issues. So these monoclonal antibodies are very important also in order to be tested in their in terms of their pureness. So you want to find out if you have a Y-shaped complete monoclonal antibody, or if you have cleavage on these antibodies and you find heavy and light change in between, or to find some fragments. All these can happen during the fermentation process due to oxidation processes and many other side reactions. So this more or less complex structure is a well-established structure to get analyzed by SEC, and what you can do with it is what we will see later on. So I mentioned at the very beginning that size exclusion chromatography is a very useful technique in order to determine proteins or monoclonal antibodies, and this is the case because because size exclusion chromatography is able to separate molecules according to its size, and that what we have discussed before, the aggregation of the protein or the oxidation of the monoclonal antibody. These are all processes ending up with substances at the end are different in size, and they can be easily observed by size exclusion chromatography. The advantage of using SEC as a method for protein analysis is most important. SEC is a non-invasive and non-destructive method. You can apply native conditions and can basically be able, if you find the right stationary phase, to measure your proteins under native conditions, and you can find out if your protein is a monomer, a dimer, a trimer, or even higher in terms of aggregation. If you want to find out these kind of aggregations, you need to have powerful separation at the beginning, and this is what we are going to talk about in the next minutes. How to improve our aggregation. What we have to avoid for our SEC analysis is any kind of interactions with our sample, our protein, our monoclonal antibody with the stationary phase. If we are able to separate our polymer or our protein only according to its size, or the fragments or the aggregates or whatever, only according to its size, without any interactions with the stationary phase, then we are on the safe side, and we can gain really reliable results in terms of protein analysis. I have mentioned before, proteins are complex molecules because of their charges they can carry on. They tend to interact with the stationary phase, so you have to make sure that your protein is not interacting with the stationary phase, but also not interacting with your column system, with your SEC system at all, so also not with the column or the capillars and so on. So you have to make sure that interactions on all cases have to be avoided or can be avoided in order to measure proteins in SEC. Therefore, your SEC system has to be prepared as a so-called biosecure SEC system on our side, meaning you're running your SEC with a complete metal-free SEC system. All your components, like the pumps, like the auto sampler, like the capillars, like the detectors, like RI and UV detectors, as well as the so-called high-end detectors, various light scattering or viscometry detectors, and even the columns, they all have to be treated in a certain way so that you avoid interaction with the protein and the surface from your materials. And this is what the PSS biosecurity system takes care for, and as well as the biosecure versions of our so-called high-end detectors. I briefly want to introduce you into GPC at all. So I mentioned before, GPC is a method that separates samples, polymers, proteins, however you want to call it, separates these according to size. And the separation of SEC is indicated here in this small video. You see that the separation takes place inside of a column indicated with the frame here. In this column are porous particles. In these particles, your samples, in this case our proteins, get separated according to size, as indicated here in this picture. Large molecules come out at the very beginning. Small molecules come out at the end, and molecules having the same size, more precisely having the same hydrodynamic volume, because this is our separation parameter. All molecules having the same hydrodynamic volume will elute at the same time from the SEC column. As larger as sample is you're going to measure, or protein is you're going to measure, as earlier it will elute from the column, as smaller it will elute later. So, and according of this type of separation according to hydrodynamic volume, according to size, we will be able to separate monomers of a protein from a dimer, a trimer, and a higher aggregation, because as higher a protein is aggregated, as larger the hydrodynamic volume of the protein will be, and as better as we are able to separate these sizes from each other, as more precisely we will be able to determine the degree of association. So if it comes to aggregation, SEC is really a method of choice because it's, as mentioned before, non-destructive, and you can run it under native conditions, and you are able to separate molecules according to its size, and for proteins according to the degree of association. When you have done so, you do not easily get any other than just an allogram, as indicated here on the lower bottom on the right-hand side. This is your primary information you get out of your SEC measurement, meaning you see when your large molecules start to elute from your column, and you see when your smallest molecules at the end will come off the column, and in between you have a degree of size from the left-hand side to the right-hand side, indicating to my allogram picture here. In order to get some molar mass information, you need to apply a calibration curve. This is done here on the upper side, on the left upper side of my slide. If you have measured protein of a given size, and you measure the retention time of these proteins of a given size, then you can combine your allogram and your retention time for the unknown protein in terms of size, and you could slice-wise, as indicated here, correlate the molar mass of these slices or to the calibration curve in the back, and then for each slice you can get your true calibration curve, and if you take an integral overall, you can calculate the overall molar mass of your unknown sample by having a calibration curve at the given column set in the background. Then you get all this information you're looking for, and not only the retention time or the elution volume. So, speaking we need to talk about how we could improve the resolution, how we could maximize the resolution, and therefore we do have a couple of parameters to talk about. It is the particle size, the porosity, the stationary phase itself, the temperature, and the flow rate. And how you can influence your resolution and improve your results, that's what I'm going to show you in the next couple of slides. So obviously it is the best recommended or the highly recommended way to make the particles as small as possible, because when you have small particles, porous particles inside of your column, then you have less interstitial volume, you have more volume, more pore volume, you get higher plate counts, and you get better results, better resolution. You can't go to very, very small particle sizes due to the fact that when the particle sizes gets too slow, I have unfortunately no time to go into detail in general, but when the particle size gets too slow, we could share our samples size-wise, and mechanical stress could also cause some instabilities to your column bed itself. So beside the fact that you also have additional high back pressure, we cannot simply reduce the particle size to below 1 nanometers, but staying about 2-3 nanometers, but staying as small as possible is very helpful for increasing the resolution, as indicated here in my next slide. What we have compared here is a mixture of various proteins, and as you can see on these on the red allogram, the protein mixture was measured on a 10 micrometer particle size Suprema column, and the same protein mixture was also measured on a 5 micrometer particle size Suprema column. The dimensions of the columns beside the size are completely identical. The column type is completely identical, and as you can easily see, comparing the blue to the red, when the particle size is getting smaller, the resolution can be improved dramatically only by varying the particle size from larger to smaller. The second step we could do to improve our resolution is not only use one column, but adding a second or even a third column of the same porosity, for example, to the first one. If we do so, we will improve the resolution by the factor of 1.4, the square root of 2. So adding a second column or a third column would further improve your resolution, but the disadvantage of this will be that you have longer elution times or retention times to wait for your results. But it can have a dramatic effect, as seen on my slide number 15, where we have compared one of the major tasks, as mentioned before. How can I separate a monomer from a dimer, a trimer of a protein in order to determine the impurities? And on the left-hand side, we do see the measurement of a protein and its dimer on just simple one column, a 5 micron Suprema column again, and you see barely indicated the dimer on this if you do the measurements on only one column. When we take two columns into account, two 100 angstrom columns, we do get the dimer 2/3 baseline separated from the monomer at the very beginning. If we would add a third column, we would get them perfectly baseline separated. But what you do also see is the disadvantage of adding a second column is that you double your analysis times from 8 milliliters to 15 milliliters, or from 8 minutes to 15 minutes if you run it at 1 mil per minute. But you really improve your resolution. The third point to improve your resolution is not only improving the particle size and adding a second column, but do also reduce the flow rate and maybe even increase the temperatures. And this is shown here, not for a protein sample because you wouldn't see it that nicely, but for a dextran and a sugar sample. The same sugar sample, dextran sample measured on a Suprema 10 micron, 100 angstrom. Then it was measured on a Suprema 5 micron, 100 angstrom. And you do even see the smaller molar masses indicated as single peaks, but taking two 100 angstrom columns together, reducing the particle size and reducing the flow rate, you do see these nice oligomeric structure for this dextran sample. It is the same sample measured on 3 different columns, and from the black to the red, for example, we have reduced the particle size and we have increased the separation distance and have reduced the flow rate from 1 mil to 0.25 mil per minute in order to get a perfect separation of oligomers as good as it possible. This would also be very helpful for protein separation if you want to separate monomers from dimers, trimers, but I'm going to show you later on some more examples on this. The latest point we can improve in order to improve our results is the column type itself. So we at PSS, we do have 2 different column types available for protein analysis. The one is a silica-based and the other one is a polymer-based material. The silica-based material indicated with the red color here, the PSS Suprema column, is on the left-hand side compared to a polymer, the Suprema-based column I have introduced to you before. And what we have measured here were base pairs DNA fragments, high molar mass DNA fragments, first of all measured under the same conditions on a polymer-based material, and then, which is the blue one, and then measured under on a silica-based material, which is, and the results for the silica-based materials are given here as the red allogram. And as you can see, for the base pairs are much better separated on the silica-based material as it is on the polymer-based material. And secondly, if I take the silica-based material and reduce the flow rate, this is shown on the right-hand side, I can further increase the resolution according to the theory of the SEC. You see the variation of the flow rate from 1 mil per minute down to 0.1 mil per minute, and it shows how nicely you can improve your resolution for these various base pairs DNA fragment. But you have to take into account doing so and reducing the flow rate by a factor of 10 would also end up with a 10 times longer retention time. But it depends what you want to see, what you want to learn about your sample in order, if you want to go for these high resolution information, or if you stay with the information you only get from 1 mil per minute, having less resolution in the background. Latest for this example, I'm going to show you again the separation for the silica-based column type 1 mil per minute, which is the black allogram shown for the protein. And you do see very nicely the separation of the monomer, the highest peaks on the low molar mass side from a dimer, the trimer, and even indicated some higher aggregates at the end of these allograms on the high molar mass side. Compared to the silica-based material, the PSS Suprema, you do see what a polymer-based material could deliver, and for 1 mil per minute, the comparable flow rate to the silica-based material, you see for the polymer-based material, the blue allogram hardly indicated the dimer beside the monomer. If you reduce the flow rate, you do see the dimer more pronounced, but not as nicely as you could see this on the Protima silica-based column. What you do see here as an improvement of the resolution, this is what I would just want to notice at the end, is not due to the fact that there are any interactions, enthalpic interactions of my protein tends to these kind of separation of the monomer and the dimer. The reason for this separation is simply the slope of the calibration curve. The red calibration curve for the Protima 1000 angstrom column shown here is simply much flatter than the slope of the calibration curve for the Suprema column, which is much steeper. And when your calibration curve runs much flatter, your resolution increases dramatically, and this is what was reflected on these monomer, dimer, trimer separation for the proteins as shown on the slide before. Here at the end of this session, I just want to give you an overview. I do not go into detail. What are the technical specs for the PSS Suprema and the PSS Protima columns are. If you have seen or followed my talk and you saw the results for the silica and polymer-based material, you could ask, why do you even offer a Suprema column if the Protima column silica-based material is so much superior? There's basically one reason, but this is an important reason. I mentioned before that proteins need to be measured at the isoelectric point, and sometimes, depending on the protein and the structure, you have to measure your protein on a higher pH value. And silica materials, unfortunately, do have the disadvantage that they start to degrade at the pH value above 8.5. So when your isoelectric point for the protein separation is above pH of 9, it is highly recommended to do the measurement on a polymer-based material and not on a silica-based material, because it will not last very long for the separation, due to the fact that the silica bonds will break up at higher pH values. This is the reason why for the complete spectra of the protein analysis, you need to have polymer and silica-based material. You can also improve the Suprema or the polymer-based resolution by reducing particle sizes. more in order to reduce the interstitial volume. This is what we do at the moment, and we will shortly come up with smaller particle sizes in order to be comparable to the silica-based material also on the polymer-based stuff. So here are the technical specs for the silica-based protein column, and again here, highly recommended or to watch this remark. LONs with pH above 9 are not recommended to be used for the separation of proteins on a SEC column, on a silica-based SEC column, because you will destroy the column material in general. So this is the point for a self-evaluation, according to the fact that I have introduced you to the method and why SEC could be useful for separating polymers and monoclonal antibodies. And now I give you a little bit time to answer these questions.
Thank you, Torsten. So everybody, this is the, for those of you who've joined us before, this is the famous time where I get to talk a little bit again, and you get to choose answers. Again, this is going to be sort of anonymous, so we see a percentage, but we do not see your individual vote. So don't be shy. Basically, the question is, what's the primary information obtained with GPC? The molar mass of the sample, the structure of the sample, or the retention time or elution volume of the sample. Torsten and I don't get to vote, because that would be cheating, but we would try for you to vote. So what's the primary information you get with GPC SEC? Is it the molar mass of the sample, the structure of the sample, or the retention time or elution volume of the sample? I will try and see that I get about, hopefully closely to 80% of you to actually participate in this. And from what I see so far, this is going to be interesting. So go ahead, please cast your vote. And I will close the polls now, since we're over 80%. Oh, that was not what I wanted to do. There we go. I wanted to share this with you. So almost 40% of you decided that the information you're getting is the molar mass of the sample, and 61% decided it's the retention time or elution volume of the sample. And it is obviously the 61% that are correct, because the only thing SEC sees is sample coming at a specific point in time through your columns. That's what you register on your raw data chromatogram. Later on, you correlate that with some sort of calibration curve, or even with advanced detection methods like light scattering, and translate that into a molar mass. But what SEC primarily does is give you information about the elution volume or retention time of the sample. So, oops. Now I get to ask you a second question. And the question is, what's the separation parameter in SEC? Is it the structure, topology, architecture of the sample, the hydrodynamic volume, or the composition of the sample? Again, so what's the separation parameter in GPC SEC? The answers are structure, topology, architecture, hydrodynamic volume, or composition. And apparently, this was a very easy one for all of you, because I may have just mentioned it. You are separating basically by the hydrodynamic volume. So all the SEC column sees is the size of your sample in solution for that specific solvent. So you got all of you got that right. And now we have a third question to ask you, and that aims more in the direction of the protein GPC that we're talking about currently. Why is GPC a suitable and powerful method for protein and monoclonal antibody analysis? Is it because proteins can be identified, because aggregation can be monitored, or because folding can be observed? Again, Torsten and I don't get to vote, but you're more than free to cast your ballot. And from what I see here, let me at least see if we can coast above 80%. Basically, almost all of you got that right. You can monitor the aggregation. You cannot identify proteins as such, but as Torsten pointed out, you can obviously see whether you have dimer, trimer, or even higher oligomers of your, not oligomers, aggregates of your protein. And depending on the software that you're using and depending on the resolution that you have for your columns, you may actually be able to quantify the amount of dimer, trimer, and so on that you have. But bottom line, you can monitor aggregation nicely with GPC SEC. And with that, I guess we're done with the self-evaluation part, and I hand you over to Torsten again for the rest of the webinar.
Okay, thanks, Derek. Thanks, everybody, for listening so carefully so far and to answering these questions. This is also highly motivating for the representative if he gets the impression that people listen and understood something from what he tried to introduce or to present. So let's talk about protein separation in SEC now in more detail. I have taken this scheme of a protein to show you that these proteins have various hydrophobic and hydrophilic residues along the polymer chain beside the foldings. And as I have mentioned also before, that they can be charged, the proteins can be charged depending on the amino acids were used at certain pH values. So in order to measure these proteins in SEC, and I have not mentioned that very much before, is in order to measure proteins in SEC correctly, we have to avoid any kind of interaction with the protein in the stationary phase. So we have to cover the charges, we have to find the isoelectric point in order to have an overall neutral monitored molecule, or we have to add any kind of salt into our system in order to improve the ionic strength, in order to get a separation of proteins according to its size and not to any kind of interaction. And how this happens, I'm going to show you in the next slides. And these are also slides to let you know that there is no universal application in terms of mobile phase or stationary phase for protein. I have chosen 3 different typical proteins. On the left-hand side, chymotrypsin is a protein that is highly hydrophilic. On the right-hand side, DNP-L-alanine is a highly hydrophobic protein. In bovine serum albumin, it's rather hydrophilic, nor hydrophobic. And I took those 3 proteins to show you the influence of the ionic strength of your mobile phase for the protein separation. They're all measured on a PSS protein column, but let's start on the left-hand side. So on the left-hand side, when you choose a high ionic strength, this is the recommended ionic strength for a highly hydrophilic protein. You see that indicated by this red chromatogram that you do get a nicely allogrammer chromatogram, and your protein elutes nicely from the column. If you now stay with the same stationary phase, just go to lower ionic strengths, suddenly you don't see your protein anymore because it sticks to the column according to the wrong chosen mobile phase. Alternatively to this, on the right-hand side, you cannot take the message that it is always good to use a high ionic strength, because on the right-hand side, when your protein, and this is the case for the DNP-alanine, when your protein is highly hydrophobic, and you work on a too high ionic strength, then you do get the vice versa results. When the ionic strength is too high, again, the red allogram, you barely see your protein coming off the column. When you lower the ionic strength and you move towards to the blue allogram, suddenly this hydrophobic protein nicely elutes from your SEC column. So it depends strongly on the type of protein you're going to measure. It depends strongly on the isoelectric point, and that's what you have to find for certain sets of protein in order to be able to measure them properly. And you have to play around and find the best SEC measurement conditions by varying the ionic strength for you in a given on a given stationary phase to find the best conditions. There are also proteins available like the bovine albumin, as the one here in the middle. This one is neither highly hydrophobic nor highly hydrophilic. So there are certain types of proteins which can be measured under low and high ionic strength, and in both cases it gives nice results. The only difference is that the elution volume is a little bit changing as a function of the ionic strength. This is why, due to the fact that the globular structure and so the hydrodynamic volume will be influenced by the amount of salt added to your system, while the same protein can elute a little bit earlier or a little bit later, depending on the ionic strength of your system. But different to the other two proteins, the bovine albumin elutes as well under low ionic strength and as well under high ionic strength conditions. So there's measure proteins. You can easily take your proteins if you know for given proteins the molar masses, then you can try to construct a calibration curve for them. And if you do get something as indicated here in this, where you barely can see a dependency of the size of the molecules from the elution time or the elution volume of the protein, then you can be quite sure that you're not under robust SEC conditions to measure proteins. And in this case, a whole bunch of various proteins were measured on a 300 angstrom column on a phosphate buffer system at pH 6. But you cannot really use these proteins as a protein calibration curve because they are not really elute according to the size dependence of the SEC. What we did next, we did increase the ionic strength by adding a certain amount of sodium chloride. We did add 0.3 mole sodium chloride, and suddenly the calibration curve starts to look more like an SEC calibration curve, and more of the proteins start to elute according to its size. So and not according to any kind of interactions. So it goes to it goes towards the right direction. The protein polarity influences still the separation for some of them. So what we did as next, we did further increase the ionic strength as indicated here on in this red line. So we increased the sodium chloride concentration up to a 0.5 or sometimes even 0.6 molar ionic strength concentration. We did stay with the pH of 6 as a phosphate buffer, and suddenly a whole bunch of proteins did stay nicely on a calibration curve and elute under SEC conditions, meaning getting separated according to size. And how nicely they can get separated is shown here on a Proteima 5 micron 100 and on a Proteima 5 micron 300 angstrom column. A certain set of protein, a selected set of protein having more or less comparable isoelectric points under the given conditions can be used to create SEC calibration curves in order to get molar mass estimations or information about unknown proteins. So again, you have to improve your methods in order to get the molar mass information or the SEC conditions as pure SEC separation according to size and no interaction. If you want to measure proteins after you have improved and optimized your separation, you need to have a detection. And the most common detectors for proteins is a UV detector, because most of the proteins are very UV active. But if you want to have a deeper insight and a more depthful information about your proteins, you can also add some more so-called molar mass sensitive detectors. And what molar mass sensitive detectors do are indicated here in this slide. A concentration detector, based on the equation here down on the left-hand side, a concentration detector shows a signal intensity only depending on a sample constant like the dn over dc, the specific refractive index, or the extinction coefficient for UV, and the concentration. As higher your concentration, as higher your signal intensity will be. Adding a molar mass sensitive detector, you do get an additional information, because as the name indicates, a molar mass sensitive detector is not only from the signal intensity depending on the on the concentration as indicated by this equation here, but also by the molar mass, and as well by the specific refractive index as a sample constant. But here we do get the second information, meaning the signal intensity as a function of the size or the molar mass of the molecule. This is the reason why we call light scattering detectors and visco detectors molar mass sensitive detectors, and RI and UV detectors concentration detectors. The dependence on the signal intensity either only on the concentration or on the concentration times the molar mass. That's the difference. And what can we use this for? Before we come to these results, here this is a scheme how the experimental setup looks like. So we have the column, the optimized column for the separation. Then we have our molar mass sensitive detector, light scattering detector, and we have a concentration detector at the end. And we do get molar mass and also structure informations out of these coupling experiments when we add those two detectors at the end, dividing the concentration signal by the light scattering signal, we end up with the molar mass information. So we can, using this technique, to determine the molar mass of an unknown protein under certain conditions. Depending on the size of the protein, you can measure according to the Rayleigh ratio, as indicated even at the equation above, out of your scattering intensity, the molar mass of your sample. And this whole scheme shows you that you have to have a powerful separation on the front end, which is the column, in order to get a more detailed information after separation about your sample by using two or more detectors. A light scattering detector is indicated here. A light scattering detector allows you the measurement of the structure information. It also allows you the measurement of the molar mass versus the structure information, and also some branching information. So I don't go into detail. I just want to show you how these instruments looks like. And a multi-angle light scattering instrument means you measure the light scattering signal at various detector observation angles at the same time. Then you can measure your radius of gyration out of it. Gives you structure information. When you're not using a light scattering detector but using a viscometer, which is the measurement of the intrinsic viscosity of your solvent, then you do get additional molar mass and structure informations and hydrodynamic volume informations, because of the fact that the intrinsic viscosity as the measurement value you get out of a viscometry experiment is 1 over the density of a molecule. This can be for aggregation determination very important, and that's what I'm going to show you at the end. Having in mind that for associations of proteins, meaning dimers, trimers, and higher aggregates, the density of the sample would stay constantly. This is what we can use in order to differentiate an association to a denaturated sample. Now let's show some light scattering SEC coupling experiments. This sample shows pretty nicely why a light scattering detector is a useful additional information for to add to an SEC setup, because the concentration signal, which is given here in the black line, shows the monomer, the dimer, and the trimer, but cannot show you much more of the higher aggregates because of the less of the sensitivities and the low amount of the higher aggregates. But the light scattering detector can nicely separate a monomer from a dimer and a trimer and a tetramer and a pentamer, because as higher the aggregation gets, as higher the light scattering signal gets, because the light scattering signal strongly depends on the molar mass of your sample, and this is increasing when your aggregation is increasing. So having a perfect separation by adding a couple of columns in a row, like here 2 times Protema 100 angstrom columns, and having a molar mass sensitive detector beside the concentration detector gives you much deeper insight about your protein impurities in terms of dimers, trimers, and higher aggregation in the combination of the light scattering and viscometry and the light scattering detector in combination with the GPC instrumentation. And here another very powerful example. If your sample is large enough and you do analyze your protein, you can easily get out of one shot, and in a SEC, MALS, or light scattering combination experiment, first of all, the protein molar mass out of the light scattering detector. You can quantify the monomer, the dimer, and the trimer out of the concentration signal. And using a MALS detector, you can even get some information about the protein size when the radius of gyration can be detected for larger molecules. And this information shown on this slide is what you get out of one single shot, one injection, having a separation and a high-end detector, light scattering detector at the end. Now coming to the monoclonal antibodies again, I have introduced this stuff before, just briefly. When you have a monoclonal antibody and this is fermented, then you can end up with a heavy chain or a light chain, and for IgB, for these heavy chain and these light chains are different in molar mass. You have 50 kilodaltons for the heavy chain and 25 kilodaltons for the light chain. So these are definitely different in size, can be easily detected by a light scattering or by an SEC experiment. And you can also detect if you have a monomer or an aggregation of 2 or 3 of these antibodies conjugated together, or you can also detect at the end if you have fragments as indicated here, because they are all different in size and should be able to be measured by an SEC experiment. Here, this is a simple SEC experiment for a monoclonal antibody, and as you can see here, as explained from me on the page before, for a certain monoclonal antibody, you see the fragments on the low molar mass fragments on the right-hand side, and you see the higher aggregates on the left-hand side, where these monoclonal antibodies as total length antibodies were aggregated, and in the middle, the red allogram shows you a full-length monoclonal antibody divided in a monomer and a dimer, and a tiny amount of the fractions. Again, secondly, if we add a light scattering detector to this, we will also get some more detailed information about the aggregates, because the light scattering detector gives an enhanced signal on the high molar mass aggregates. Why? Because the light scattering detector shows the high molar mass aggregates more pronounced. And on the right hand side down here, you can also see this nicely shift for an increase of the signal intensity when you go from concentration detector, which is the red and the blue one, to a light scattering detector, which is the green one. You see the dimers much more pronounced compared to the other ones. You can also use the SEC to separate hydrolysates of proteins, and when you do a hydrolysation of a protein, you end up with the amino acids. And if you choose your SEC conditions in a way that you run it in a mixed mode, that you get these amino acids which are not so different in size, but you get them separated from each other, and you inject the amino acids you assume to be part of this protein, as indicated here in this slide. You can identify the arginine, the phenylalanine, the tryptosine, and the leucine easily as part of the hydrolyzed lactalbumin bovine hydrolyzed protein. So even amino acid separation can be done and can be used SEC can be used to get some amino acid informations after hydrolysation. At the very end of my talk, I would like to show you how powerful SEC Maltz coupling can be used in order to measure protein dynamics. The question where taking two proteins, thyroglobulin and bovine serum albumin, and put them under stress. If you put the protein under stress, it should denaturate, it should shift from your globular structure to your denaturated structure. And as indicated by this picture, when this takes place, a protein increases its size. If a protein increases its size in the denaturated state, this should easily be detectable by SEC because we separate according to size. So we did put our proteins under stress, and we wanted to measure the denaturation for the protein. And we did this by a various temperature program for the two proteins. And what happens is what I'm going to show you here. At the very beginning, at 25 degrees Celsius, we had our protein indicated by this red colored line. We had the monomer, the dimer, and the trimer. And then we heated up our protein 30 minutes to 50 degrees, 60 minutes to 50 degrees, and 120 minutes to 50 degrees. And as you can see, and we again did measure under this given experimental conditions a protein later on, our monomer decreases as a function of time as heated at a certain temperature. And we did get some higher amounts of aggregated or whatever high molar mass proteins, but we weren't quite sure, are these aggregations or is this a denaturation? So for the thyroglobulin, we did also measure the radius of gyration dependency, and again, the radius of gyration for the monomer were decreasing, also indicated by the decreasing amount here of the monomer with a certain radius of gyration. And for this higher aggregated sample, the radius for this high molar mass, or early eluting, so to say, early eluting substance, the radius of the gyration did increase. So we have two indications. The molar mass did increase, and the radius of gyration did increase. This could also be shown by the 90-degree light scattering signal. Nicely, the light scattering signal got larger and larger at this aggregated stage. So we were quite positive that there was something going on with our protein, but we were still not sure. We were assuming that it was a kind of an aggregation, not the denaturation, but we weren't quite sure yet. monomer were increasing, radius of gyration were increasing. We did the same for the bovine serum albumin. We did the same experiment. We did also heat up this, and we did also see an increase of the molar mass as a function of stress under the protein. As shown here, at the beginning there was a monomer, a dimer, and a trimer, and after the heating process, the stress of the protein, we suddenly lost the dimers and the trimers. We ended up with this early eluting high molar mass stuff with a really increasing molar mass, and also with a decreasing monomer. So there was something going on, but we still weren't quite sure if we really had, as indicated by these results so far, that we really had a kind of aggregation or association and not a denaturation. It looked like an association, aggregation, but we could not finally prove it before we did start to do the final proof by taking this analogy for our protein. When we go to the denaturation, when we denaturate our protein from a globular to the denaturated state, then the density of the protein should decrease. While when we would end up only with an aggregation of the protein, due to the fact that the density of the globular state stays the same, the density of the overall aggregated molecule should also stay the same. And the density, as mentioned before, can easily be measured by a viscometry experiment. So we took our tyroglobulin, did do the same type of experiment by heating and stressing our protein, and we did measure the density or the intrinsic viscosity of our protein as 1 over density. And beside the fact that we again did see this high molar mass sample, we did not see any change of the intrinsic viscosity. We did not see any change of the density of our molecule, and we compared our protein results with so-called random coil results, which is these pink-colored pullulan polysaccharide samples having much higher intrinsic viscosities at the same elution volume as the comparable protein sample. So if the density stays that low compared to a random coil polymer, this was the final proof that we did stress our protein, but we did not denaturate our protein. The protein covered itself by aggregation before denaturation. So we could finally prove by using an SEC light scattering, using an SEC viscometry experiment, that you can use it for study protein dynamics, and we could prove under native conditions, when a protein got stressed and measured under native conditions, that the protein is not denaturating before aggregation, before aggregation, and protein aggregates to higher units in order to protect themselves from aggregation. So this brings me to the end, and I hope I could show you that SEC is a very powerful method to separate proteins. If you do it properly, you can measure protein aggregations, protein dimers, trimers, and higher-mers. And if you add molar mass sensitive detectors to the proteins, if you couple a light scattering or viscometer detector to the proteins, you do even get additional structure information of your proteins that help you to a deeper understanding what happens in the dynamic of your protein. For example, if you stress your protein, as indicated in my final results before. Thank you very much for your kind attention and listening to me. And last but not least, I just want to wish all of you a very Merry Christmas and a Happy New Year, and I'm more than open to answer your questions. Thanks a lot.
Thank you, Torsten, for this Nice presentation. However, we're basically running out of time, so I hope that we can answer one or two short questions. You mentioned that if a protein is large enough, you could actually get some information on the radius of gyration and light scattering. And the question there is, what is large enough?
The radius of gyration should be above 10 nanometer.
Okay, so that's good. And then the follow-up question to that, since you also introduced the viscosity detector, is there an advantage or disadvantage of using one over the other to get the data? Because obviously out of the viscosity experiment you can get the hydrodynamic volume, which also is an indication of the size in solution. So is there an advantage or disadvantage of using the viscosity detector over the light scattering detector, or the other way around?
Again, the light scattering detector can be used when the protein is large enough and you want to get this radius of gyration information. Above 10 nanometer size of the protein, the light scattering detector would not give you any radius of gyration information. So for smaller molecules, as long as you do see, as long as the signal intensity is high enough, you can use the light scattering detector for molar mass determination. Radius of gyration information, the protein has to be large enough. And viscometry will also work for smaller size proteins.
Thank you. And then I think we can try and squeeze in one last kind of question. Is it possible to distinguish between the same antibodies which only have different glycosylation profiles?
Not really. As long as they are equal in size, they would elute at the same time. In order to get this measured, in order to get this question answered, I would not use SEC. I would use a different technique, a liquid adsorption chromatography under critical conditions, maybe, in order to, then you could answer these questions as well. Only measuring two different antibodies, they're only different in the functionalization. This will not work with the SEC.
Thank you. And then one question that I would like to put in here, because I think it's crucial, is how can you actually differentiate if you detect, let's say, smaller species and larger species? How can you make sure that these are aggregates and not denaturalized proteins? So how can you differentiate between aggregates and denaturalized proteins?
That's what I showed in my last example. When you measure the, first of all, you get the elution volume and indicating this is a high molar mass stuff coming off the column. The light scattering could show you an increased light scattering signal, but in order to make sure, and for a denatured sample, if it would be denaturation and not aggregation, the light scattering signal would not increase because the denatured protein still has the same mass, so you would measure the same molar mass for the denatured as you would measure for the globular protein. If the molar mass is increasing, this indicates you that you have an aggregation at the early elution volumes. And secondly, adding a viscometer and measuring the intrinsic viscosity and finding out if the intrinsic viscosity is the same or different between the early eluting sample and the late eluting sample, because the globular structure would elute late and the denatured would elute earlier. So for a denatured sample, you would find no change in molar mass, but a different intrinsic viscosity, as you would find for the globular state. And for an aggregate, you would find a constant intrinsic viscosity and an increasing molar mass.
Thank you, Torsten. I think this pretty much brings us to the end. So to sum up, for those of you who are still here and still joining us, I sent out a chat message with Torsten's and my email address. So if you would like to request a PDF of the slides that Torsten presented today, you're more than welcome to send us an email. This also goes, obviously, for any questions you may have later on after digesting the slides or the recording of the webinar. Again, I would like to thank all of you for joining us this morning, afternoon, evening. And thank you again, Torsten, for your presentation. I would like to wish everyone a good day, good night, good afternoon, wherever in the world you are. And I will leave the last words to Torsten.
Yeah, I also would like to thank for all of you staying so long. At least for some of you, maybe it's also late. Here in Germany, we have now 10 minutes past 6. Sorry that it took a little bit longer, but as Derek mentioned, I'm normally always too long with my talks. Sorry about this. Thanks for staying. And again, as I mentioned before, if you have any further questions, just send us an email. Oh, by the way, I did not show my last slide indicating here where you see Derek's and my email address. Whenever you feel like and you have additional questions, send us an email. We more than helpful try to answer them. And as mentioned before, this is it from me. Have a nice evening, nice night, and very Merry Christmas and Happy New Year to everybody.